Hey everybody, in this AP Chem series video, we're going to take a look at how an acid's molecular structure can impact its strength. First, remember that we've already seen strong acids or stronger acids have very large Ka values and will make lots of H3O+ and conjugate base A-, whereas weaker acids have smaller Ka values, producing less H3O+ and less conjugate base A-. In this video, we'll also come across some seemingly unrelated topics such as the trend in atomic radius and electronegativity. So let's get started by looking at some of the connections between molecular structure and acid strength. There's really two factors to consider. One of them is the strength of the bond between the hydrogen and the rest of the acid that we'll just generally call A. It's also affected by the stability of the conjugate base that's produced. If the bond between the hydrogen and the rest of the acid is very weak, then that means that's a very easy bond to break. So it's therefore very easy to remove that hydrogen that makes that hydrogen more ionizable. That means more acid molecules will lose their hydrogen. You're going to end up with a stronger acid. The opposite is true as well. If there's a stronger bond, it results in a weaker acid. In terms of conjugate base stability, you could say that a more stable conjugate base results in an acid that prefers to be in its conjugate base form. So more of the acid molecules will ionize to be in that form. You're going to end up with a stronger acid that way too. Of course, the opposite is true here as well. And these statements make up some of the key ideas for this video. Make sure to pause and take some time to write those down. Lastly, we'll go one level deeper and look at some of the factors related to this bond strength and conjugate base stability. For bond strength, there's two things we need to evaluate. One is the bond polarity, and the other is the length of the bond. For conjugate base stability, we're going to be looking at resonance structures and electronegativity. So we'll start off by taking a closer look at the length of the bond and say that long bond, so that's a very long bond between the hydrogen and the rest of the acid, that's also going to be a very weak bond. And again, if it's a weak bond, it's easier to ionize that hydrogen away. You're going to end up with a stronger acid. You can see that pattern played out with these four acid examples. Let's compare the weakest acid on the list, HF, to the strongest HI. From this model, you can see that fluorine has a much smaller radius. Iodine's radius is much larger. This tells me that the bond length between H and F is very short compared to a longer bond length in HI. Like we just clarified, if the bond is longer, it's also weaker, so the hydrogen is more ionizable in the HI molecule, and that explains HI being the strongest acid on this list. This is another key idea for this video. Make sure to take a minute and write that down. We should also say that bond length is only going to be considered when you have large differences in bond length, like there are with these four acid molecules. If you're comparing acids that have similar bond lengths, however, you're going to instead compare their polarities. Increased polarity is actually a weaker bond, making it easier to ionize that hydrogen and giving you a stronger acid. We can see that play out in these four examples, again ranked in terms of acid strength, CH4 the weakest, HF the strongest. Let's compare NH3 to HF and explain some of these differences. If you consider the electronegativities of N and H, they are different, but it's not a huge difference. So this bond is polar, but not very polar. Compared to the difference in electronegativity between H and F, which is much greater, that is a much more polar bond. Like we just said, a more polar bond is also a weaker bond. That means that hydrogen is easier to ionize from the fluorine, and that's why HF is the stronger acid. We can also explain this difference another way. Let's look at the hydrolysis reactions for NH3 and HF, both donating NH+ over to water, producing H3O+ and their conjugate base. Instead of focusing on the acid molecules themselves, we're instead going to focus on their conjugate bases. If the negative charge in a conjugate base is present on a more electronegative atom, it actually has a stabilizing effect on that conjugate base, and it's going to lead to a stronger acid. In terms of these two conjugate bases, we can look at F- then and say that fluorine is more electronegative than nitrogen, making the F- more stable, meaning the HF is going to ionize into its conjugate base more than the NH3 will, making HF a stronger acid. These are our final two key ideas for this video. Take some time, write those down. That also wraps it up for this video. Thanks a lot for watching, and here is a brief summary.